Hello everyone, my name is Sotthiwat Ekanut. Today I will present about partially encrypted multi-party computation. This method can prevent the duplicate from gradient attack, which try to reconstruct the original data of the individual participant. Here is the outline of my presentation. First, I will introduce why we need to preserve the privacy in federated learning and the existing problem that inspire us to propose our method. We propose the partially encrypted multi-party computation for federated learning to solve the existing problem. We also provide the experimental result to support our idea. In general, we have already known that the great model or neural network need to use massive data to improve the model accuracy. Unfortunately, there are many issues that prevent the deep learning to train on the massive data. First, it is an island of data. The data of each organization is located in different country and region. So as a result, we cannot train a model based on those data. Second, there is a regulation which published by European Union to prevent transferring the data outside the Europe as a GDPR policy. And it also clarifies about how the personal information should be processed to protect the data leakage. Not only about the policy, but the customer also worry about transferring the data outside of that machine. Here is a two example that leak the user information. First, the Lazada leaked 1.1 million user information. And second example, the Facebook also leaked 419 million user information in 2019. In the general machine learning, when we would like to get a great model, one directly way is that using the centralized learning. In this technique, it will collect the data from different participants and then train a model based on those data. However, like I mentioned earlier, it is not safe to do that. So that is an approach that obtains the similar accuracy without transferring the data to a central server. The federated learning is firstly introduced by Google in 2016. It's able to achieve a similar performance like a centralized learning, but without transferring the data. I summarize the workflow of the federated learning in the right figure. So first, the central server initiates the global model and publish those global model to the participant. Then participant will train the global model based on the local dataset. And after finish the training, the participant will uploading the local model to the central server. And the central server will evaluating the local model to obtain the new global model, which have already learned the data from all participants. From our base knowledge, there are two attacks which can reconstruct the training data accurately. First, the attack name as a deep leakage from gradient. The assumption is that the central server is honest but curious, so it still follows the protocol honestly, but curious about the training image in the machine. So if you use any information that obtained from the local participant to reconstruct the training image, and the information that it obtained from the participant is the gradient update from local participant. So the main idea is summarized on the live figure. After the client finish the training line and upload the gradient update to the central server, right now the central server will know the gradient of the victim. To perform the attack, the curious server generated the dummy image and a dummy label. Then it passed those to the global model and obtained the dummy gradient. So this is the goal of the adversary. They will optimize the dummy image and dummy label in the direction that minimizing the differentiate between the dummy gradient and the truth gradient. When the dummy gradient are near or closer to the truth gradient light, the dummy image and dummy label will be reconstructed accurately, as you can see on the left figure. And in the malicious column, this is a attack of the previous mechanism, which using GAN to reconstruct But as you can see that it does not accurate and can reconstruct the class representative only. And there are another attack named as improved duplicate from gradient. This will observe that the previous method cannot reconstruct the label correctly. So they propose a method that can extract the global label with a 100%, as you can see on the right figure, on the right table. They check the size of the last hidden layer to extract the ground truth label. And the conversion speed of this attack is faster than the previous attack, as you can see on figure. The right figure is a IDLG and the left figure is a DLG. From those attacks, it motivates us to propose the efficiency defense mechanism because the existing method require the high computation cost to encrypt the weight parameter or the local gradient update, such as a multi-party computation or encryption key. To avoid the high communication, some work propose to use the randomness mechanism to preserve the privacy, such as differential privacy, but this method maybe reduce the model accuracy. So we define the solution requirements. First, it needs to prevent the attack using gradient update to reconstruct the training data with the low communication cost and efficiency when the number of the client is increased. And ideally, it should not have any accuracy drop. So our method, instead of encrypting the whole gradient update, right, we will encrypt the critical part of the local gradient update only to preserve the privacy of the training data. So right now, the gradient is split into two types, type A and type B. On the type A, the client need to apply the MPC on the gradient type A, and for the type B, the local participant can submit the gradient type B directly to the central server without any encryption. After we using additive secret sharing MPC protocol on the gradient type A, right? The local client will get the M secret share and then it will send each secret share to another participant, as you can see on the figure. And after all participants receive the secret share from all, it will aggregate those together as a local aggregation value and then upload it to the central server. After the central server obtains the local aggregation value from all participants, it will sum them up together, and the summing value will equal to the aggregation of the gradient type A without any MPC. This shows that the central server able to obtain the global gradient type A without knowing the ground truth of the gradient type A on each participant. This figure illustrates the overview of our framework. The upper is a central server and the lower is a local participant who join the training process. The local participant will train the global model first and then obtain a gradient update. And then right now it's split into two types, type A and type B. And on type A, it needs to apply the MPC, right? So you need to exchanging the secret share and then aggregating those together and then upload the gradient to the central server. Then the central server will averaging the local update and obtain a new global update and publish those to all participants. Then the client will update the local model based on the global update that come from the central server. So the question is, which is a hidden layer that should be a type A gradient? So in our paper, the first hidden layer should be the gradient type A. We provide the theoretical analysis and the experimental results show that the first hidden layer should be encrypted to prevent DLG and IDLG. This slide will show the theoretical analysis about the PE-MPC, prevent DLG and IDLG. Using those attacks when the first hidden layer, which composed of N node, is encrypted, the curious server able to obtain the output of the first hidden layer accurately. Why? Because it already has the gradient updates of the second hidden layer to the last hidden layer. So let me denote the equation on the first hidden layer first. The left is a activation function and the right is a linear system for the weight and the bias. Like I said earlier, the QLS server had already obtained Y. And so the QLS server also know about the activation function, right? So it can obtain the output of the first hidden layer before the activation function accurately. And right now, the weight of the parameter also known and the bias too. So the only variable that need to reconstruct is a variable x. In this paper, we assume that the input of the vector x has more than n non-zero element. So we claim that for the linear system, the solution for x have an infinity number when d is greater than n. For the example, the dimensionality of the input data is more than the input of the number of the neuron in the first hidden layer. To validate the effectiveness of the PEMPC in terms of the prediction accuracy comparison, we using a MNIST dataset and Sotthiwat dataset. We use a Lineage 5 and VGT16 to predict the result. And the ADAM is an optimizer that we use on both models. And the global training law is a 100, and the local training law in each participant is a 5 law only. And the samples are randomly distributed to all participants. So the data distribution is a IID. In this experiment, there are 10 local clients joint training in every round. There are 4 methods which are evaluated. First, the centralized learning, and second, the non-MPC, when the federated learning does not use any MPC. And the third one, full MPC, when it uses a MPC on all gradient update. And the last one is our proposed method. As you can see on the left figure, the convergence speed and the test accuracy of the federated learning is slightly slower than the centralized learning, a few iterations only. Interestingly, the training loss and the accuracy when the federated learning apply MPC and not apply are almost identical. So we can prevent DLG and IDLG without sacrificing the model accuracy. And in this experiment, we evaluate the communication costs that occur in one local participant by 3 methods: non-MPC, PEMPC, and full MPC, like the previous slide. On the left figure, we evaluate on the MNIST dataset the communication cost in the first 2 rounds. X-axis is the number of the training round, and Y-axis is the size of the transmitted data in each round. So our proposed method PEMPC only increase the size allow 45 kilobyte only. However, when we see about the size of the transmitted data in full MPC method, it increase allow 20 times non-MPC. And similar result can be found on the Sotthiwat 10, as you can see on the right side. The intuition behind the significant drop is that PEMPC only encrypt the critical part only, like I mentioned earlier. And in order to evaluate the efficiency of our framework, right, we increase the number of the clients from 4 to 64 for the MNIST dataset and 2 to 32 for the Sotthiwat 10. And all hyperparameter is the same as the previous one. So as you can see right now, there are 3 methods: full MPC, non-MPC, and PEMPC. This figure will show the size of the transmitted data in one local participant. X-axis is the number client, and Y-axis is the size of the transmitted data in each round. For the full MPC method, the green line is significantly increased higher than the non-MPC blue line, and our method, the orange line. And the similar behavior can be seen in Sotthiwat 10. We also plotted the baseline method and our proposed method on the right side. For the Lineage 5 in MNIST dataset, The overhead at the client 64, the amount of data is increased around 0.3 megabyte only. And for the Cipher 10, which using VTG16, the communication overhead increased around 0.8 megabyte only when the client is 32. Our method also reduce the computation overhead because we only encrypt the first hidden layer only. In the following section, it will show that the first hidden layer contains most information and our purpose able to prevent DLG and IDLG. In order to do that, we need to reproduce the source code of the attack mechanism, DLG and IDLG. We still test on the MNIST dataset and Cipher10 dataset. And the metric that used to evaluate the successfully attack is a mean square error, which measures the error between the actual image and the reconstruct image. And for the second metric, does not include in the presentation, but you can see on the paper. In this experiment, we will show that the first hidden layer contains most information for DLG and IDLG. In order to evaluate that, we replace the gradient update on the first hidden layer with the Gaussian random number and send those to the DLG and IDLG to let them attack. And plot the mean square error. Then again, but right now we're changing to do on the second hidden layer only and pass those to DLG and IDLG. And again on the third and the last hidden layer. As you can see on the experimental result, it shows that replacing the first hidden layer will produce the largest MSE of the image. And for the last hidden layer, it produces the smallest MSE of the image. And the attack paper also proposed a defense mechanism on DLG. It used a differential privacy to preserve the gradient in local gradient. However, the experimental showed that the amount of the Gaussian and Laplacian noise that used to protect the gradient is too much and decrease the model accuracy. In this experiment, we comparing our method with a differential privacy mechanism that adding the Gaussian and Laplacian noise. As you can see on the right figure, if the amount of noise is small, it still cannot prevent DLG and IDLG. But our method, which does not reduce any accuracy, able to hide the ground-truth image from those attacks, as you can see in the red box. And the similar result can be found on the Cipher10 too. So for the conclusion, our method able to prevent DLG and IDLG to reconstruct the original image without decrease the model accuracy and has much less communication cost than the standard MPC. Thank you for your time and attention, and feel free to contact us if you have any question or comment. Thank you.